everybody. So I'm going to go through all of the Unit 7 notes. So this is going to be a long video. Feel free to, after I go through 7.1, stop the video and then start it later to continue the notes. You're going to take notes on yourself, on your own. I don't have any guided notes for you. So let's get started. Unit 7 is all about simple harmonic motion and waves. So first we're going to start with defining simple harmonic motion. So simple harmonic motion, which I'll abbreviate SHM, just to save some space, is an oscillation. An oscillation is just a repeating movement over the same path caused by some restoring force. So some force is causing something to move back and forth over the same path. So a couple of important things to be able to define. One is the period, which we've used before. That's the time for one oscillation in seconds. So the time to return to the same location and how many seconds it takes to do that. And then frequency is oscillations per second. These are inverse relationships. So the period is 1 divided by the frequency. The frequency is 1 divided by the period. The unit of frequency is the hertz, and 1 hertz is 1 per second. So like 1 oscillation per second. Cool. And there's 2 types of simple harmonic motion that we will talk about. One is a simple pendulum. So that's something, down here we've got some sort of fixed point here. And this little guy, this is a mass. It's called a bob, which is kind of funny. And it's some length of string. The period is equal to 2 pi times the square root of L, which is in meters, and G, which we know is 9.8. And that will tell you how fast it takes for the pendulum to start at point A here, swing out to point B, and then come all the way back. So 1 period is an out and then back. Only the length of the string and G affect the period of a pendulum. So if you had the same pendulum on Mars, it would swing at a different rate. And the restoring force is mg sine theta. It's the weight of the bob that is pulling it back towards the center of the swing. So just part of the weight is what's the restoring force for a simple pendulum. Right. And then the other scenario that we'll talk about is a mass on a spring. So imagine a mass that's connected to a spring. Let's say this is a frictionless surface. The period is going to equal 2 pi times the square root of m, which is the mass of the block, and k, which is the spring constant. So what that looks like, let's say we have a mass on a spring, we compress it some distance negative x. It's going to be pushed by that spring force, which is going to be our restoring force, to equilibrium, and then it'll stretch out to some maximum displacement x and then bounce back and forth. And I'm going to go kind of fast, so again, feel free to pause and copy the notes down. What happens in this scenario is we end up with a sinusoidal relationship for position, and then we'll see velocity acceleration as well. For position, let's say we've got some pendulum here. Okay. And it goes out some maximum distance, x. At the maximum, we're going to call that maximum displacement A. A is the amplitude. And that's our maximum distance from equilibrium. So we come out some distance x. This is A right here. And we're going to start at the maximum. And then we're going to swing down to the bottom. This is going to be a quarter of the way through 1 period. And then we're at 0. Once we're halfway through 1 whole oscillation, we're over here at some negative distance, negative A distance. 3/4 of the way through the period, we get back to 0. and then we end up where we started at one period. So this is one period, a maximum to a maximum, or a min to a min, just one full cycle. The position can be graphed with this equation here. X equals your amplitude times the cosine of 2 pi times the frequency times t, which is our x variable. That equation is on the AP formula sheet. And then if we think about the velocity, if any of y'all are in calculus, these will look familiar because you're going to be taking a derivative. We start at 0. Okay. Then we start moving to the left, which we'll take as a negative. So we're going to be moving the fastest at the bottom. Once we're halfway through the period, we stop momentarily and then start swinging back to the right until we get out to our maximum again. So that's what the shape of our velocity looks like. If we start with a cosine graph, our velocity will be a negative or a flipped sine graph. And then acceleration, if you think about where the force is directed, that'll help us with acceleration. So at A here, there's a component of the force that's pulling to the left, and it's going to be at a maximum, so a maximum negative acceleration initially. 0 once we get to the bottom, and then it follows that same sign pattern. It's going to be a negative cosine graph. Right, and that's it for 7.1. Moving on to 7.2, properties of waves. So we're talking about mechanical waves for this unit. Those are disturbances that propagate through matter, and that's something with mass. Next semester, we'll talk about electromagnetic waves, which are not mechanical waves, but we'll get to that later. We'll start with a transverse wave. So a transverse wave are particles move perpendicular to the disturbance. So this is kind of like an ocean wave. The wave is moving to the right, but individual water particles are moving up and down. So our velocity and our particle movement are perpendicular. Okay. Things that we can measure about a mechanical wave, we can have our amplitude here. That's our A, that's the maximum height of our wave. That would be at the measurement to the crest, or it would be the same right here to a trough. We can measure the wavelength, which is the distance for one cycle. And we can measure the wave velocity, which I'll give you some formulas down here. So amplitude is that maximum displacement is determined by the work done in creating the disturbance. So if you think about it, we're talking about the ocean still. Let's say there's an earthquake. That amplitude is going to be determined by the magnitude of the earthquake. The wavelength is the distance between waves, so one cycle distance that's measured in meters. And then we can also measure the wave velocity, which is the wavelength times the frequency. And this is controlled by the medium. So in the case of an ocean wave, it's determined by the water itself. The frequency is controlled by the source of the wave. Okay. Cool. And if our source vibrates in simple harmonic motion, the wave will be periodic. So that means that it will make that pretty sine or cosine kind of shape, and it will have a period to it. If I instead think about this like a slinky, and you've got someone's hand here that's moving up and down in simple harmonic motion, then this will be a periodic wave, and that frequency is controlled by how fast you move your hand. We also have longitudinal waves. This one's a little bit funkier to think about. So I like to think about a stretched slinky, and then if you were to push parallel to the slinky, you'll end up with a little wave that travels back and forth. The particle movement in this case is parallel to the wave itself. So the wavelength is going to be from a compression to another compression, or from an expansion, which is called a rarefaction, to a rarefaction. Sound is a longitudinal wave. If you are talking over here, what you're doing is compressing air molecules together. That compression is traveling through the air. I talked about the slinky already. And then there's certain types of earthquake waves, P waves, that travel longitudinally. Oops. Waves can be reflected. So when a wave reaches the end of a medium, it is reflected. So here I've got pictures of different types of waves on a string. If you actually go to PhET, I don't know if it's .com, it might be .org, but anyways, look up PhET and look up waves on a string, and you'll be able to see this a little bit better. So if there's a fixed end, what'll happen, the wave comes in, it hits this fixed end, this could be like a hand or just some sort of fixed point, and it will exert a force on the rope and it will make it flip to the other side, and it will be reflected on the opposite side of the rope. But if it's not fixed, what happens is it essentially goes up and then reflects without inverting. And then wave interference. So when two waves pass through the same location, they will either add together or cancel each other out. So if I have A and B, let's say A is 1 block high and B is 2 blocks high, they will combine to be 3 blocks high, and then they'll keep going in their original directions. They will not reflect off each other. But if let's say we have A is -1 high and B is a half high, when they combine together, they will end up with a smaller wave, and then keep moving on their ways. Okay. All right, that's it for 7.2. Let's move on to 7.3. 7.3, we're going to talk about standing waves. So standing waves appear to be stationary due to identical waves traveling in opposite directions. So this can be due to, if we have a string, you have a wave and it bounces and then reflects, and it's going to make this shape, and if you move it fast enough, it's going to look like it's just kind of one continuous wave. So here's an example of a rope that is fixed at one end. We oscillate one end of the rope, the other is fixed, and if we move it at the right frequency, it will create a standing wave. You can see this with a string or a slinky if you have one at home and want to play with it. The areas where we have constructive interference, and it makes that largest distance, that's called an antinode. That's our max amplitude. And then where it appears to be stationary, that is a node, and that's called by destructive interference. So objects have a natural frequency. It's the frequency an object tends to vibrate when disturbed. You can see this if you looked inside of a piano, you have different strings of different widths, and they oscillate at a different natural frequency. So that's how you get different notes. Okay. Cool. And the fundamental frequency is the lowest frequency that will produce a standing wave with the fewest nodes and antinodes. So if you have a string and you make it look kind of like a jump rope, kind of like I drew up here, where you have 2 nodes and 1 antinode, whatever frequency that is, that's our fundamental frequency, because that's the least amount of nodes and antinodes, if that makes sense. Cool. So let me actually see if I can pull up a video real quick. We're going to look up standing wave video. So let me play this. I don't need you to talk. There we go. So there's a video of a standing wave that's got a node at either end and then 2 antinodes. See if I can get it to look cooler. Okay, and then here's one where it's vibrating faster and it's got more nodes and antinodes, but it appears to be stationary. That's what I wanted to show you. All right, so for a rope that has 2 fixed ends, the fundamental frequency is going to be half of a wavelength. So a full wavelength would look something like that. So you've got essentially one full period. So if we cut that in half, that is half of a wavelength. So the length of the string equals half of the wavelength. And it's got a 1 there. It's called the first harmonic or the fundamental frequency. And then if we increase the frequency until we have two antinodes and 3 nodes, that is called the second harmonic. And that is 1 full wavelength. So the length of the string equals 1 wavelength. We can keep increasing the frequency, and that'll become the third harmonic. This is 1.5 wavelengths. So the length of the string equals 3 halves of that third harmonic wavelength. So the length of the string equals n/2, where n is the harmonic number, times the wavelength. So that's our formula for a rope with 2 fixed ends. The frequencies double from one harmonic to another. So as we move up, the frequencies are doubling. All right, now we're on to 7.4, our last topic. So this is all about sound and resonance. Sound is a longitudinal wave, as I mentioned earlier. The frequency is equal to, not equal to, but it relates to the pitch. So a higher frequency is a higher pitch. Humans can usually hear between 20 and 20,000 hertz. Anything less than 20 is called infrasonic, and anything over 20,000 is ultrasonic. The speed of sound depends on the material, which the material would be air. So in 20 degrees Celsius air, that's kind of our room temperature starting point, it's going to be 343 meters per second. So that's how fast sound travels. So we can have standing waves with sound. Standing waves, sound can create standing waves in a confined space, or a pipe, or a flute, something like that, when there is an antinode at the opening. And what happens then is it causes resonance. The constructive interference causes an increase in the amplitude or the loudness of the sound. So this is how not most, but a lot of musical instruments work. It creates standing waves in pipes, so like a flute or a saxophone. There's antinodes at the opening, and so it resonates and creates a louder sound. So we've got 2 different types of resonance. We can have an open tube resonance and then a closed tube, which I'll show you in a minute. For an open tube, we need to have an antinode, so that biggest, so it's going technically it would look like there's a rarefaction, and then a compression would be a node, and then another rarefaction, because this is sound. But I'm going to draw it like a transverse wave because it's easier to picture and easier to draw. So we've got antinodes at the openings, and then a node in the middle. So this is half of a wavelength. So remember, a wavelength is, it could be from here to here, or it could be from here to here. Again, so it's a expansion or refraction here, and then a compression in the middle. So that's half of a wavelength for the first harmonic. The second harmonic is a full wavelength, kind of going from that max to max here. So the open tube looks opposite of a fixed string, but it has the same relationship where the length of the pipe is equal to n/2 times the wavelength, where n is the harmonic number. And again, the frequency is going to be doubling here, which is going to be related to an octave if you are familiar with music. A closed tube, on the other hand, is a little bit different. To bounce off of the closed part of the tube here, we need to have a node. And then we have to have an antinode at the opening. So this right here is a quarter of a full wavelength. The length of the pipe is a quarter of the wavelength for the first harmonic. But then we can't actually have another harmonic until we have another opening here. So we're not doubling. We're actually going to be going up to the third harmonic. So the third harmonic is the length of the pipe is 3/4 of a wavelength. Just because if we go up by quarters, we'd end up right here where we have a node and a node, and it would not resonate. So for here, the length of the string is n over 4 times the wavelength, where n is only odd harmonic numbers. And it says same as a loose string right here. We didn't really talk about that, so you can ignore that. All right, and the last thing we're going to talk about, a few like random odds and ends for sound. One of those is the Doppler effect, and that is when the frequency changes due to movement. So this could be either you are moving towards something that's making sound, or something that's making sound is moving towards you. So if we have a stationary object, it emits sound waves in all directions, and they're all equidistant from each other. But then if we start moving that object, what happens is the sound waves moving behind the object get stretched out, and the sound waves in front get compressed. And since the wavelength here decreases, the frequency is going to increase, and it sounds higher pitched. You may have heard this if you ever have heard a like a siren moving towards you. So you have a police car or an ambulance moving towards you. It sounds higher pitched until it passes you, and then it sounds lower pitched. And then last idea here is the idea of beats. So if you have slightly different frequencies, just a few hertz, it'll cause periods of constructive and destructive interference that alternate. So it makes this kind of funky, loud and soft pattern, and that's called a beat. So here I've got two frequencies that are a little bit different, but then they